The other option is to open up Maple. Okay, under math programs, if you're at a lab, Maple 17. All right, and then once you have that link saved on the hard drive or wherever, you can open it through Maple. So open, search in desktop, and find that Maple. Where'd it go? Right there. Okay. So you got to save the link first to the hard drive or your flash drive or something.
So you mean open netbook test for the next one? So I'd use Maple.
Maybe it might be able to done it or something. But no, these things are slow. It would maybe
crash the server and we're trying to use it on something.
Like I showed you, you only have to change the differential equation definition. So right here, that's x prime of t. You just need to change that. And then this one is the y prime of t. You just need to change that expression. So you put those two in there, and then accordingly, if you have an initial condition, just change those values here. Okay, and then just hit enter.
What's that?
I'm a little stuck here on what the hell it is.
All right, so you could try that thing before. So if you differentiate this one,
okay,
call it equation 1, then you'd have something involving y prime, right? If you solve that equation for y prime, so over here, once you differentiate this, solve it for y prime and replace that over there, then you have an equation only involving x. You might be able to solve that.
Okay, so I'm going to
So try that. Differentiate this one, and you'll get something
with respect to t. You said
with respect to t.
Okay.
Mm-hmm.
All right.
As long as your other one's 1. Yeah, I put my cosine first. All right, fair enough.
I've been doing engineering good, so like I'm having a little bit of a whiplash on it. It's just engineering 101.
What's up, Doug?
I'm sorry.
Solid state. I like that. Solid state.
I think we got it.
Hey, Nick, do you want to be in our project?
1A. 2, unless you have a laptop with you, this is going to be something you have to do at home or a computer lab. But let's look at number 3 and then take a break. So write the following equation. This is a single second-order linear differential equation. But we're going to write it as a system of first order, so that the order will be smaller, strangely. Another way to think about this is resolve. We're going to resolve it into a system.
Kind of like using the reduction method.
Kind of, yeah. If I remember, if my memory of that is correct. So we're going to resolve this single equation into a system of smaller equations. So going off what we did before, So what do we want to call it? Y? Yeah, we can call it Y. Let Y represent X for a moment. That's a dependent variable. Then Y prime, or sorry, let's let, Y prime would be X prime. Wait, let me see here. No, I'm going to let Y1 equals X. That's how I want to do it. All right. And capture X prime with another one, Y2. So call Y2 X prime. But notice X prime is the same as Y1 prime. Okay, that's a 1, that's a prime. That gets ugly. And let Y2 equal X double prime.
Y3?
Oh, Y3, sorry.
I just want to keep these 2's, 3's,
X
and
double
5's
prime.
straight.
And X double prime, that's X prime prime, so that'd be Y2 prime. Okay. And then one thing that we can say about X double prime, note, X double prime, which we just called Y3, is equal to, and I'm going to clear this equation out, on the other side, negative 4x minus 3x prime, right? But now with those variables that we created, negative 4x, that's negative 4y1, minus 3, and x prime is y2. Okay. So the system becomes, and what we do is we write them in the primes first. So y1 prime is equal to y2. And I'm going to put these spaces here just because we are going to be using matrices soon enough. y2 prime equals y3. And this guy, this is confusing. So y2 prime is x double prime, right? y2 prime is the same as x double prime, that's y3. So y2 double prime. Or no, wait. No, that's 3 again. God.
It's always 3.
It's like Valve, we can just ignore 3 and use 4 if you want.
What happened here? So y3 is x double prime, which is the same as y2 prime. But this is y1 prime. That's why we got y1 prime equals y2. y2 prime. Yeah, and y3 is all that bit. So y3 is just negative 4y1. And I'm trying to put this far enough out so it's like, and y1 prime is y2. Okay, so y2 prime, same as y3, but it's negative 4y1 minus 3y2. So that would be the system.
So it's just writing it in terms of one variable.
Now we can just do any of the same way we would do with the last one.
Yeah.
Differentiate one. So it is essentially the reduction method where you make a substitution that, t is equal to y prime and then t prime is equal to y double prime, so you can resolve it.
Or you could think of this as a 0 y1 right there, and then I got all my terms. This looks like y1, y2 prime, 0, 1, negative 4, negative 3, y1, y2 in linear algebra notation. All right, so let's go ahead and take a break. Let's start back. We'll start in 10 minutes, 3 o'clock. Yeah, we got an hour, 50 minutes to go through linear algebra.
I think you can do it.
If we already took linear, does that mean that,
And this will be familiar.
You are free to go home.
This is college, you don't even have to be here, dude. Like,
Okay.
If you're not going to just learn this on your own.
All right, let's go ahead and get started. 5. So 4.1 is an intro, and you know, the way you could write some of these things, if you resolve a single differential equation even into a system, well, you can write it like this way in terms of matrices and a column vector of unknowns, right? So we are moving in that direction. So we're going to do some review for some of you, an intro for others of you into linear algebra. All right, so matrices and how we can handle differential equations involving, using matrices. All right, so to get started, a matrix. In particular, M by N. All right, so an M by N matrix has nothing to do with Keanu Reeves. It is an M by N array. An array of elements. Now, they could be just constants. They could also be functions. That's why they use the term elements, because you could have a matrix of functions. We've seen that when we found the Wronskian. You could have a matrix of partial derivatives, like we did in Calc 4 for the second derivative test. But so anyway, it's an array of elements arranged into M rows and N columns. Okay, so in that order, number of rows, number of columns, M by N matrix. So how many numbers or entries are there going to be?
Times N.
M times N, right? M rows of N. There will be Mn entries or elements. Okay. All right. So generic. You usually use letters like A and B, C, capitals for matrices. But a matrix is just, now if I put in this notation, row followed by column, this is entry A11, row 1, column 1. A12, dot, 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 A1, and how many columns are there? N. A sub 1n, all right. And then the second row would be entry 21. A22, so row 2, column 2, A2n. All right, and we don't know, this is just general, don't know how many rows there are. So say there's M rows, this would go down to the mth row, so M1 would be mth row, first column. A sub M2, dot, 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 all the way out to A sub Mn. All right, so you got M rows, N columns, and we usually put that around it, make a matrix, okay? All right, so some quick examples. By no means does M have to be equal to N. Okay? If they are, then we call it a square matrix for obvious reasons, but you could have any number of rows and columns. So say A is this matrix, say 2, -1, 5, 0, 10, 2. Okay, what would be the dimensions? 2 by 3 matrix. All right, what about if I had this one? Yeah, 3 by 3, that's what we call the zero matrix. Okay, just all entries are zeros. We're going to define matrix addition in a moment, things like that. So yeah, this is the zero matrix, 3 by 3, order 3 zero matrix. All right, so operations that can be done with them define. To add matrices or subtract. All right. Now, one thing to add or subtract they have to have the same dimensions. Okay, so for instance, I can't add a 2x3 and a 3x3 matrix because I don't have the same entries, the same, I don't have the same dimensions. Okay, so these have to have the same dimensions. All right, so both n by n, whatever that happens to be. All right, so an example, let's take that A matrix, 2, -1, 5, 0, 10, 2, and define the matrix B to be, all right, let's call it C. We'll use B for other things later. So say the matrix C is 5, 2, 8 along the first row, -1, 0, 4. All right, so these are both 2 by 3. Now, how do we define the vector, or sorry, the matrix sum A plus C? Right. Yeah, A 1, 2 plus C 1, 2. A 1, 3 plus C 1, 3. So we add, basically, we just add corresponding entries. So if you know how to add numbers, you know how to add matrices. That's why they have to match in dimensions. So literally, I'm going to write this once, but it's just 2 plus 5 in the first entry. -1 plus 2, 5 plus 8. So we replace the sum is just the sum of the individual corresponding entries. 0 plus -1, 10 plus 0, 2 plus 4. So we get what? 7, 1, 13, -1, 10, 6. So it's literally just kind of component-wise addition, like vectors, right? You can think of a vector and in terms of a column. Three-dimensional vector could be thought of as a 3 by 1 matrix. You can add 2 three-dimensional vectors by adding corresponding components. Okay. So this is just, yeah, just component-wise addition. Okay. We can also talk about scalar multiplication, just like scalar multiplication of a vector. All right. So say I have 5 times, and we use that same matrix A. All right. So how do you think this is going to go? All right, it's 5 times 2, -1, 5, 0, 10, 2. And each component, each entry, gets multiplied by that scalar. So we're going to get 10, -5, 25, 0, 50, 10. Okay, so each entry gets scaled, right? All right. Gets scaled by that scalar. That's repetitive. All right, what else can be done with matrices? I don't want to talk about multiplication quite yet. We can multiply 2 matrices, but that's a little bit different. Okay.
Transposition?
Transposition? Mm-hmm. Yeah, you can find the transpose of a matrix, and it doesn't have to be square or anything like that. So the transpose of a matrix. Okay, transpose of a matrix is just the matrix that results when you interchange the rows and columns of a, or take the rows and turn them into the columns of the transpose matrix. So interchanged so that, and I'll use some indexing, so that, for instance, in general, the ith row of A just becomes the ith column of its transpose. And the way we do it, any matrix A, we denote its transpose by A and a superscript with a T, transpose. Okay. So again, with our matrix A being 2, -1, 5, 0, 10, -2, what would A transpose be? So the ith row becomes the ith column. The first row would become the first column. So take that row and just make it a column.
And switch.
2, -1, 5, right. And the second row becomes the second column.
0, 10.
0, 10, -2. And yeah, how are the dimensions related? What's the dimension of this guy originally?
2 by 3.
2 by 3. What is the dimension of its transpose?
3 by 2.
3 by 2.
Does this come in effect when you have two different matrices, you know, like one's a 2 by 3 and another one's a 3 by 2, and you want to change it so you can do operation? Or what's the purpose of this?
This makes them, now all of a sudden, we haven't talked about this, but you can multiply any matrix and its transpose because then the dimensions fit correctly.
Okay.
We're going to talk about multiplication in a second, but the number of columns in the first vector has to match the number of rows of the second vector to multiply them. And if I transpose the rows and columns, then I can multiply any matrix by its transpose because then its dimensions match.
Okay.
And the product of a matrix and its transpose does have some meaning if you think of these as row vectors, right? And its transpose, those row vectors become column vectors. And when you multiply them, you're just basically doing the dot product of that column vector, or the row vector of A, I should say. All right, now let's talk about multiplication. You can multiply matrices, but this is a big if. Not just any two matrices. You can multiply matrices if the dimensions match. I'm going to say match correctly. That doesn't mean that they are both 2 by 3, for instance, and 2 by 3. Not equal, but they match correctly.
Can you say what you mean by that?
Yes, I will do that.
Do you mean by 2 by 3, 3 by 2, or?
That will work. Yeah. So to define multiplication, so I'm just going to say, to define the product, matrix product, A times B, in that order, we need, let's see, the number of columns in A to equal the number of rows of B. Okay. So, in general, if I'm going to multiply two matrices and A is M by P, for instance, to multiply it by another matrix, row, columns, the number of columns in this one has to match the number of rows here. So it has to have the same number, same dimension there. Say matrix B is P by N or something. As long as they match, okay? Number of columns in A and the number of rows in B. So we'll define that as the product, P. All right, and in this case, the entry in that product matrix, P, All right, and it's always hard to do this with words. We'll do it with an example to illustrate, and then it becomes kind of easier. So the entry Pij of the product, right, the matrix product, is, this is how I think I define it. It's the dot product of the ith row of A All right, so the ith row of A with the jth row of B. Okay, if you think of the rows of A as vectors, right, and the columns of B, then if you're finding a dot product, where you multiply corresponding entries and then add all the results. And we're going to do one to. What's that? Did I say two rows? Ith row of A and the jth column of B. That one should be called. I knew to bring my pencil today. Okay, so let's do an example. Our trusty A matrix, we're going to keep it as 2, -1, 5. 0, 10, 2. Again, that's a 3 by 2. Oh, no, it's not. 2 by 3, sorry. Rows, columns. I always had strange memorization techniques when I took linear algebra. Rows before columns when we talk about the dimensions. 2 by 3. Row before column, R before C. If you write out RC, just like RC Cola. Okay, that'll help you. RC Cola, that's how I remember it. Rows, columns. So it's a 2 by 3.
Rank and file also refers to row and column on a chessboard. Just
Oh, okay. Okay.
because one's letters, one's numbers.
And say B is this matrix entries 5, 0, 6, -1, 2, -2, 1, 1, 0. Okay. And what is this one? Entry. The dimensions of this guy is a square. It's a 3 by 3 matrix. All right. And this is how I do it. I remember it. A times B, I can only multiply them if the number of columns in A matches up with the number of rows in B. So those have to match, those inside dimensions. Okay? So, A times B. The way I define a piece of Ij, it's just a matrix of entries of the form Pij, where each entry, Pij, is the dot product of the ith row of A with the jth column of B. Okay, so it goes this way. Go across A and down B. So, the 1, 1 entry of this product is the first row of A dotted with the first column of B. Okay? So, as I go across with my left hand, I'm going down with my right hand, and I'm multiplying corresponding entries. So what do we get here? 10 plus 1 plus 5. 16. All right, so check it out. Row 1, column 2 of my product comes from row 1, column 2 of my original 2 matrices. Row 1, column 2 will give me entry 1, 2. So 1, 2, multiply, this is a dot product of these two 3-dimensional vectors. 0, -2, plus 5. So what do we get? 3? All right, and then my 3, 1 entry, 1, 3, row 1, column 3 comes from row 1, column 3. Dot product, 12, so 2 times 6 is 12, plus 2, that's 14, plus 0. All right, need a little more room on this guy. All right, and Now I move on to the next row.